All right, hey, eighth graders, we are going to jump into page, this is page 4 in your math binder. So if you are sitting in class right now or at home, it doesn't really matter. You are on page 4 in your math binder. It looks like this. It's got a 4 in the corner. It's got some pictures in the middle, and I want you to follow along completely. That means you should have a pencil in your hand. You should have page 4 pulled out of your math binder or in your math binder, however it's easiest for you to write. And you are going to write down every single thing that you see Ms. Johnson write down on this screen here. So looking at these first two problems, these are a bit of review from when Ms. McGowan was talking about the squares. So this first one says draw a square with a rational side length. Number 2 says draw a square with an irrational side length. Your job is to find the area of those and to find the side length. So go ahead and give these two a shot. If you can figure them out, that's awesome. We're going to go over it in just a moment, so you can push pause. Try to draw a rational side length and an irrational side length square. All right, now some of you totally knew how to do that, and that's awesome. Others of you might have looked at the screen and said, what did she just ask me to do? I'm going to push play to figure out. Great, we're going to go over these ones. Now, a rational side length means that that side length has a finite number. It terminates, it either repeats or it terminates. So we can write this answer as a fraction, but what we saw when we were looking at the squares was it looked something kind of like this. Now, what makes the square that I just drew on here rational is if I count this side, it is 1, 2, 3, 4, 5 distances long on every side of this square. So if I know that that's 5 distances long on all sides, I can also say that there are 1, 2, 3, 4, 5, 10, 15, 20, 25 squares on the inside. Sorry, this guy's weed whacking out here, and of course, it's just really loud. Okay, so what's the area of that square that I just wrote? The area of that square is, I know I put this on here. It's right there. Don't you love it when technology, hold on, let me see if I can figure this out. I'm gonna pause it. Okay, I think I figured it out. So as I look at this now, the area of that square is 25 units squared. Remember, you're counting squares on the inside. That's why we have units squared rather than just units. Now, we said that the side length is always the square root of the area. So if I were to, where's my pen? If I were to find the square root of this area, it would look something like this. I'd be saying square root of 25. Now, most of you know what the square root of 25 is because 25 is a perfect square, but I am actually going to pop over here to my calculator, and I'm going to type in square root, which is right here, of 25. And look, the answer shows up on the other side, and it says that my answer is 5. So when I did the side length as the square root of the area, I know that my side length should be 5 units. Okay, and that is a rational number, which means that I followed the criteria given at the top here where it said draw a square with a rational side length. Let's look at number 2 where it says draw a square with an irrational side length. So on number 2, I don't want it to be one of these nice, beautiful, perfect, straight up and down squares. I'm going to do one that is tilted. So I drew a tilted square that looks like this. Now yours could look exactly like this, or yours could be tilted slightly differently. And you saw the other day how Ms. McGowan showed you that you could break this thing up. So I am going to remind you how we broke this up the other day. We said you could draw a line coming across and going up. Ooh, this is very difficult to do. You're going to see how wonderful my penmanship is on a computer. I could do that. I could bring this one over here, and I could go up here. And when I find the area of these things, I know that this top green triangle up here is 1, 2, 3, 4, 5 by 2. So 5 times 2 is 10. And if I divide that in half, it is 5. Now, all of these are going to be 5 by 2 triangles. So 5 times 2 is always 10. And when I take half of that, it's always 5. So 5, 10, 15, and 20. And then in the interior, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I add this all up, 5, 10, 15, 20, plus the 9 squares in the center, I know that the area of this thing is 29 units squared. And then remember, side length is always the square root of the area. So if I were to begin, I might say, okay, I'm taking the square root of 29. Let me see what that is. Over here, I'm going to type in square root of 29. Look at that thing. 5.385164807. That is not rational. And you might be thinking, oh crap, I messed up on this. No, you didn't. We were looking for an irrational side length. That's good. We wanted that to happen. So rather than writing down that 5 point blah, 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 I'm actually just going to write down square root of 29 units. Now, yes, that square root doesn't go over the whole thing. That's because technology, but I put this U at the end to notate that it was units. We didn't actually have a real measurement on that one. Okay, so let's look at this next little section. We are going to talk about something that I believe you've seen this picture in the 7th grade in Ms. Dyer, Ms. Olson's 7th grade math classes. So we're going to fill in this figure with the names, definitions, and examples of different sorts of number systems. So a long, long time ago, back when they came up with numbers, they needed numbers for very basic things. The first things that people wanted to do were be able to count things. So actually, like ancient Babylonians is where we saw some of the first numerical systems, and they looked very different than they look today. But it's actually in an ingredients list where people brewed beer. That's where they counted amounts and numbers so that they could brew this alcohol properly so it wouldn't murder people with the wrong amounts of fermented barley. So a long time ago, they needed those numbers so they could count. And the original counting numbers are actually called natural numbers. You're going to put that in the most inner circle there. The natural numbers start at 1, and it's the numbers that we count with. So 1, 2, 3, 4, 5, 6, blah, 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 blah. That comma, dot, dot, dot means that the pattern continues on in the same way indefinitely, forever. Okay, so the natural numbers were great. However, there was something missing from the natural numbers. There's actually quite a bit missing from the natural numbers, but the big thing was sometimes you don't have anything. And sometimes you can't start by saying, I've got 1 case of barley, or I've got 1 sheep. You sometimes have 0 sheep. I'm guessing many of you in this classroom have 0 cases of barley at home or 0 sheep at home. So the whole numbers are the next set. And I want you to write out whole numbers and put this example beneath, because the whole numbers are everything from the natural numbers plus a 0. It's kind of a silly, small distinction between 2 entire sets of numbers, is just putting that 0 in there. But now when we added the 0 in, we could talk about having nothing, because having nothing is technically an amount of something. It's just none of it. That's kind of a brain puzzler. Okay, so we've got the natural numbers, which is the counting numbers, the whole numbers, add a 0 in there, and then after the whole numbers, there were also some numbers that we needed to be able to talk about when counting ingredients and when counting animals, and so on. We needed to be able to talk about negative numbers. So twist your paper sideways so you can, or maybe you're talented enough to just write this and it fits, but we're going to put integers in there. Integers are the next set of number, and they include all the natural numbers and then the 0 from the whole numbers, but then they take the natural numbers and go negative, because negative amounts were a real thing, and they still are a real thing. You can have negative something. That's called debt. So you can owe someone barley or a sheep or whatever, and that would mean that you actually have less than 0. You need to repay someone the amount that you have. Negative numbers come in very handy when we're talking about things like temperature, because you can drop below 0. Trust me, I'm from Minnesota and it's very, very cold there. Like negative 30 sometimes. It's horrible. But we need those negative numbers so that we can talk about those distances below 0 or those amounts below nothing. Okay, so we've got natural numbers, which are counting numbers, whole numbers including 0, integers, throw in the negatives, but sometimes even integers don't cover everything. So we needed another set of numbers that included the numbers between the integers. And those numbers are fractions and decimals. Those are our rational numbers. So rational numbers include all of these other numbers, counting, 0, negatives, but they also add in terminating, which means stopping, or repeating decimals. And I thought there was something else here, but apparently there is not. Another thing that I might write in for rational, when we're talking about terminating and repeating decimals, another thing that often comes up is fractions. Now, decimals and fractions can be switched back and forth, but every time we see something that is a fraction, you know it's going to be rational. All right. So we've got terminating, which means decimals that stop, like 1.5 or 1.234. And repeating is anything that's got the bar for repeating on the top of it. And fractions, you know what a fraction looks like. Okay, we've got another set over here. Now notice all these other ones kind of like enveloped one another. This is like sad little lonely island of misfit toys. The stuff over here doesn't fit in this other category. It's different. It's actually different than rational. It's very different from rational, so much so that we call it irrational. Irrational numbers go over here. Now, if rational numbers terminated, means stop, or repeated, irrational numbers are going to be the opposite of that. Irrational numbers never terminate. That means they never end, and they also never repeat. Now, we've seen some irrational numbers before. The number pi, yes, it's a number and a food, but in this case, it's going to be the number 3.14579, blah, 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 blah. It goes on and on forever and ever and ever. Now, some of you might be thinking, oh, pi does stop. Well, let's look. If I put pi on here, on this calculator, it's 3.141592654. You're right, it did stop on here, but that's because this computer screen is apparently too dumb to know that it goes on and on and on and on forever. So oftentimes your calculator is going to round the very end so that it shows you an approximation for whatever it is. So the other one that was on here was square root of 27. When I type in square root of 27, you're going to get an approximation, but you'll see there's no pattern here. 5.196152423, that does not repeat, and the one that we'll show you would terminate fairly quickly on here. So try not to let that frighten you too much. So this was non-terminating and non-repeating, and I believe if I click, oh, never mind. Just ignore that. Okay, so now I'm going to go back to this page. The other one here is E. That is another number kind of like pi. It's a constant, 2.71 or something like that, and it goes on and on forever. So we've got rational numbers, we've got irrational numbers, and these all fall under the bigger category of real numbers. People always think that when I say real numbers, it sounds weird because what's the opposite of that? Fake numbers? No, actually, the opposite of real numbers, wait for it, they're actually called imaginary numbers. So the real numbers include rationals, irrationals, integers, whole numbers, natural numbers, and the non-real numbers would be what we call imaginary numbers. And if you're feeling really excited about imaginary numbers, just wait till you get to like number theory. But an example of an imaginary number would be if you were to try to take the square root of -1. So if I come over here and I type in square root, and let's see, I don't know where the negative is on here. Square root of, hold on, I'm gonna pause it and see. Okay, remember how I paused it because I wasn't sure what I was doing? Okay, I figured out how to type in a negative. It was really simple. I just typed in the subtraction sign on my keyboard, which it worked like 2 seconds ago. There we go. Square root of -1. Watch what happens. Undefined, boo. Some calculators might even tell you error. That's because these calculators cannot handle an imaginary number. They can't handle it, but it's a whole idea that we're not going to go through in the 8th grade. So just know that imaginary numbers exist, but we're not talking about them for a very long time in math. So, oops, there we go. All right, we've got all these ideas. All you need to know is this rational numbers over here on the left and the irrational numbers. And we're going to look at the distinction between those two within the bigger realm of real numbers. Okay, so let's do a couple examples, and we're going to see if we can figure out if something is rational or irrational using that chart that we just had a moment ago. So number 3 is the number of people wearing glasses in your classes. So if you were to look around the room right now, which some of you are at home, so there's probably just you in the room, but imagine a real classroom. The number of people wearing glasses, what category would that fit under? I'm going to eliminate one right off the bat. It's not an irrational number because we're not going to have like 3.14159 people wearing glasses in a classroom. It's always going to be an actual number. A lot of times there's like 3 or 4 or 1 people in the room, 1 person in the room who's wearing glasses, and that could be a natural number because it's a counting number. But I have been in rooms before where nobody in the room is wearing glasses, which would mean we'd have to use 0, which is a whole number. So there are 2 different options here. It could be the natural counting numbers, or it could be a whole number, including 0. Write that down for number 3. Number 4 is asking us to identify the set of number that best describes the circumference of different sized circular plates. Now to find circumference, you need to use pi. And when you're using pi and you're multiplying by pi, that's an irrational number. So that would mean that this answer would be irrational. It involves pi. Irrational. I have the hiccups. It's gonna be really annoying. Okay, number 5, the amount of water in a glass as it evaporates. Now if I actually am holding a glass, but it's a delicious glass of not water. If I were holding this glass and slowly this Diet Coke were to start evaporating, you would have like the full amount, the 44 ounces, and then it would start to drop and drop and drop, but you'd hit every single number in between. You would hit all these positive numbers and you keep going, you'd keep going. In between every number, you'd hit all the numbers in between. Like when you get to 4 ounces, you drop down to 3 ounces. And somewhere in there, since you hit every single amount, you would actually cross by pi because pi is between 3 and 4. So in the end, you'd hit every single rational number, every single irrational number. You'd actually hit all numbers in existence because you'd have to evaporate all the way down. That's real numbers. Boom, all of them. Constant evaporation would include all types of numbers from the top down. Okay, lastly, the weight of a person in pounds. If you've ever looked at a scale before, scales always have a decimal or a fraction, I guess. Maybe there's some scales that do fractions. I've never seen one. But those decimals always stop. And if I go back to this page before, hold on. If I go back to this page before, terminating or repeating decimals fall under rational numbers. And on a scale, it'll usually say like 150 point blah, 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 blah. But it doesn't say point blah, 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 repeating bar. This is rational because it's a decimal that stops or a fraction. All right, we're gonna look at one more set of examples. Determine whether each number is rational or irrational. I'm gonna have you pause this. It should only take you about like 3 minutes, and I want you to write rational or irrational for each of these 7 through 14. So each of these, is that 8 problems? Rational or irrational. And I didn't even ask you to write down why. Pause the screen, see if you can do it. Okay, hopefully you paused it. We're gonna go over these. -3. -3 was in the integers, which makes this a rational number. Also, it terminates, it stops. It doesn't go on and on forever without ending or without any pattern. So this one terminates, it's rational. Okay, number 8. It's a fraction, everybody. Fractions are rational. That's all there is to it. We wrote that in the section of rational. Okay, number 9. 2 times pi, irrational. Remember, pi is always non-terminating, non-repeating, but let me show you what that looks like when I type in 2 times pi. And by the way, when they're next to each other like this, that means they're being multiplied, like 2x would mean 2 times x. So if I type in 2 times pi, which is pi, look over there on the right side. That definitely doesn't look like this number stops. It's 6.283185307. So whenever we multiply by pi or add pi on, you're gonna have an irrational number because pi was irrational and it likes to make everybody around it irrational. Kind of like a little sibling sometimes. Okay, number 10, again, there's a fraction there. That makes it rational. Number 11 has a decimal, but notice that decimal has a repeating bar above it. If it's a repeating decimal, it is rational. Number 12, square root of 36. If I come back over here and I type in square root of 36, bam, look at that answer, it is 6. So every time you see a square root, that does not make it irrational. This square root actually does equal 6, which terminates, that's just a whole number, and that is rational. Okay, now let's look at negative square root of 42. Now some of you might be saying, that's imaginary, it's got a negative. Well, the negative here is on the outside. So this is actually just negative square root, and then I can type in 42. So it's not undefined. This one, though, doesn't look like it has any sort of pattern, and it doesn't stop. So that would make this one irrational. We would say that it doesn't terminate, non-terminating, never stops, and also it's non-repeating, because if I look at that pattern here, none of these numbers repeat over and over and over again. It's not like 6.4848484848. Okay, last one, negative 4.8. Notice that decimal stops after 0.8. That's a terminating decimal, which makes this one rational. Okay, we got through this. So you can take this page of notes now. Please kindly put it back in your binder, and you can move on. And the awkward part where I find the stop.